Hello everyone, the question is what is the splitting pattern in tetrahedral geometry? The most asked questions for the competitive exams are octahedral and tetrahedral geometries. These are the most basic geometries which we commonly come across in the transition metal complexes. In the octahedral geometry, T2G set and EG set, that is the splitting pattern, 3 orbitals will be having lower energy and 2 orbitals will be having higher energy. When we come to tetrahedra, the splitting pattern is little bit different. Because whenever we consider a tetrahedral geometry, in this tetrahedral geometry, we consider that the ligands are present at the corners of a cube and the metal is present at the center of a cube. So if I consider one ligand to be present here, second ligand to be present here, third will be away from you, fourth will be towards you. And supposing that the metal is present here, this is like away from you, this is towards you. Well, this is tetrahedral geometry. In this tetrahedral geometry, if at all I consider the coordinate axis, suppose if I consider this as the y-axis, no ligand is falling along the y-axis. If I consider this as z-axis, no ligand is along the z-axis. This is towards you. It is not along the z-axis. And if I consider this as x-axis, which is pointing towards you and away from you, no ligand is falling along the y-axis. So the conclusion is, let me consider this as x-axis and consider this as y-axis. These are just conventions. Whatever you can consider, you can. But by convention, generally we will take this as x-axis, this as y-axis, and this as z-axis. So whatever ligands that are present, these ligands are not falling along the axis, they are in between the axis. In the octahedral geometry, whatever ligands that are coming or whatever ligands that are approaching the metal, all the ligands approach along the axis. And along the axis, we have two orbitals which we call them as axial orbitals, dz square and dx square minus y square. They are raised in energy. But in tetrahedral geometry, no ligand is approaching along the axis, and these ligands, they make two different angles with respect to the 5 d orbitals present on the metal. So before the ligands approach, all the 5 d orbitals of the metal will be degenerate. But once the ligands approach and when it is forming a geometry, these ligands will be forming two different angles with the 5 d orbitals. And that effect we call it as angular effect. Angular effect. One angle is approximately half of tetrahedral angle, approximately 54 degree. Another angle will be 1/3 of tetrahedral angle. So it will be approximately 36 degree. Tetrahedral angle, we know it is 109.5 degree or 109 degree 28 minutes. So one angle is about half of the tetrahedral angle, one angle is about 1/3 of the tetrahedral angle. Whichever angle is larger, 54 degree, it means these ligands are away from the orbitals by an angle of 54 degree. These ligands are away from the orbitals by an angle of 36 degree. It means these are much closer than these orbitals. So the orbitals which are making 36 degree angle with the ligands, they will be having greater repulsions in comparison with the orbital which is making 54 degree angle. Now altogether, let us consider the splitting pattern. In the splitting pattern, we always begin from the 5 degenerate orbitals. These 5 orbitals, I can consider them as dz square, dxy, dxz, dyz, dx square minus y square. These are splitting into two different energy levels, the lower energy level and a higher energy level. there is a barycenter or the center of gravity. The lower set we have dz square, dx square minus y square, and the higher set we have dxy, dxz and dyz. The below set we assign symmetry labeling to them. According to the symmetry labeling, the below set is called as E set and the above set is called as T2 set, just as octahedra. But one change is, in the tetrahedra, the geometry itself does not contain center of inversion. When the geometry itself does not contain center of inversion, though d-orbitals has center of inversion, parity should not be shown. Every d-orbital will have inversion, but first of all you have to check for the geometry. Octahedral geometry has center of inversion. D-orbitals also have center of inversion. Therefore, we end the label with G. Parity will be G-rad. Whereas in the tetrahedra, the geometry itself do not contain any inversion. Therefore, we should not end with parity G. Simply we have to leave it as E and T2. E means double degeneracy. T is triple degeneracy. 2 is with respect to absence of vertical plane or absence of a secondary axis. Well, any electron that enters into E set, this will stabilize the system by minus 0.6 delta T or minus 6 dq, and any electron which enters into T2 set, it will stabilize the system, it will destabilize the system by 0.4 delta O or 4 dq. This is destabilization. So any electron that enters into E set will stabilize the system by 0.6 or 6 dq. Any electron which enters into T2 set will destabilize the system by 0.4 delta T or 4 dq. Okay, stabilization energy is given in negatives. Therefore, we have assigned negative. Okay, this is about tetrahedral splitting. In tetrahedral splitting, we have a small change with respect to or in comparison to octahedra. Here we have angular effect, two different angles. No ligand is approaching along the axis. Therefore, tetrahedral splitting is very much weaker in comparison to octahedral splitting. It is almost half of octahedral splitting. It is 4/9 of the octahedral splitting. Thank you.